Welcome to Sleepy Science Student, where we explore the cosmos one peaceful breath at a time. Tonight, we're going on a slow, soothing journey into the realm of space travel. How we leave our home planet, drift through the void, and venture into the infinite darkness beyond. It's a story of physics and dreams, of metal and mathematics, of human curiosity reaching gently toward the stars. I hope this video isn't too interesting. Though if it does happen to keep you awake, at least you'll be learning something fascinating about humanity's most ambitious adventure, not the worst way to spend a sleepless night. Before we launch into the cosmos together, I'd love it if you gave this video a like and maybe even subscribed if you haven't already. It really helps this peaceful little channel grow and means more curious minds can find their way here, gently, one by one. I'd also love to know where you're watching from and what time it is for you right now. Are you tuning in from a cozy bed in Houston at midnight, perhaps near where Mission Control once guided astronauts to the moon? Or are you listening from a couch in Mumbai at noon, taking a quiet break while the world bustles outside? Let me know in the comments. It's always such a joy to see this gentle community of learners scattered softly across the globe, all of us looking up at the same stars. Now, settle in. Get comfortable. You don't need to remember any of this. You don't need to take notes or stay alert for a quiz. Just let the words wash over you like solar wind sweeping through space. Invisible, gentle, persistent. Let your shoulders relax. Let your breathing slow. And as we begin this tranquil voyage beyond Earth's atmosphere, remember this video is for educational and relaxation purposes only. It's not intended as medical advice, astronaut training, or a substitute for actual rocket science degrees, though it might make you dream of floating peacefully among the stars. Ready? Let's begin. Let's talk about dreams. Not the kind that visit you in sleep, though those are lovely too, but the kind that humans have carried in their hearts for thousands of years. The dream of leaving Earth. The dream of touching the sky and then going beyond it, into that vast darkness peppered with lights. For most of human history, this was pure fantasy. People looked up at birds and felt a gentle envy. Birds could escape the ground whenever they wished, riding invisible currents of air, free from Earth's patient pull. We watched them with wonder, these casual masters of the third dimension, and we ached quietly to join them. It's a bit like watching someone swim when you've never learned how. You see them gliding effortlessly through water, and you want that same grace, that same freedom. For centuries, we wanted to swim through the sky. Early attempts at flight were charmingly optimistic and often tragically unsuccessful. People strapped feathered wings to their arms and leaped from towers, flapping desperately. The universe, as always, remained polite but firm in its physical laws. Humans were not shaped for flight the way birds were. We were too heavy, our muscles too weak, our understanding of aerodynamics too incomplete. Gravity always won these early debates, gently but decisively. But here's something remarkable about humans. We're stubborn in the gentlest possible way. We keep trying. We observe, we think, we experiment, and slowly, we learn. Each failure teaches us something. Each crashed contraption reveals another piece of the puzzle. Then, one cold December morning in 1903, two brothers from Ohio did something extraordinary near the sand dunes of Kitty Hawk. The Wright Brothers achieved controlled, sustained flight in a heavier-than-air machine. It lasted 12 seconds. The aircraft traveled 120 feet. In the vast scope of human history, it was the blink of an eye. But in that blink, everything changed. You might think that 12 seconds doesn't sound particularly impressive, but consider this. It was 12 seconds of humans doing something that, for all of our existence up to that point, we simply couldn't do. It was proof. It was possibility made real. It was the gentle beginning of a journey that would eventually take us not just above the ground, not just through the clouds, but completely off the planet. From those 12 seconds in 1903, we managed to reach the moon in just 66 years. 66 years. It's barely a human lifetime. Someone born the year the Wright brothers first flew could have watched Neil Armstrong's boot touch lunar dust. The universe, it seems, rewards persistence. But flight through Earth's atmosphere, remarkable as it is only the beginning of our story tonight. Flying within the air is one thing. Leaving the air entirely, leaving Earth itself, is something else altogether. It requires not just wings and propellers, but a complete reimagining of what's possible. Space, you see, doesn't play by the same gentle rules as the sky. In the sky, you have air to push against, air to generate lift, air to breathe. In space, there is none of that. Space is not just empty, it's profoundly, almost aggressively empty. It's the absence of almost everything we take for granted. To travel there, we needed to invent something entirely new. We needed rockets. And so, quietly, patiently, through the early and middle parts of the 20th century, brilliant minds around the world began to figure out how to escape Earth entirely. Some of these minds worked in universities, some in deserts, some in secret military programs. They built on centuries of physics and chemistry and mathematics. They made mistakes. They had explosions. So many explosions. Metal twisted, fire bloomed, dreams crashed into testing grounds. But slowly, the knowledge accumulated. Slowly, the rockets got better. And then, one day in 1961, a Russian pilot named Yuri Gagarin climbed into a capsule atop a towering pillar of explosive fuel and became the first human to leave Earth and return alive. Can you imagine that moment? The courage it must have taken. No one had ever done this before. No one knew for certain what would happen to a human body beyond Earth's protective embrace. But Gagarin went anyway, riding fire and mathematics into the void, and when he came back and opened the capsule hatch, he was smiling. The dream of flight, it turned out, was just the first chapter. The real story, the story we're exploring together tonight, is about what came after. It's about how we learned to leave our planet, how we learned to survive in the hostile emptiness beyond, and how we continue to push gently, persistently, into the darkness, driven by curiosity and wonder, and that ancient human stubbornness that refuses to accept limits. Space travel is not just engineering, though there's plenty of elegant engineering involved. It's not just physics, though. Physics governs every moment. It's a testament to what humans can do when we combine knowledge with courage, when we point at the impossible and quietly say, let's try anyway. So, tonight, we're going to explore how it all works. We'll talk about the rockets that carry us up, the mathematics that keep us from falling back down, the systems that keep us alive in an environment that very much wants us dead, and the dreams that keep us reaching for worlds beyond our own. But we'll do it slowly, gently, with plenty of time to let each idea settle into your mind like moon dust onto regolith. Take a breath. We have time. The universe has been waiting for billions of years. It can wait a little longer while we understand it properly. Now, let's talk about rockets. These magnificent, thundering towers of metal and fuel that somehow lift us away from our planet. At first glance, they seem impossibly complex, and in their details they certainly are. But the basic principle, that's wonderfully, almost disappointingly simple. A rocket works by throwing things backward very, very fast. That's it. That's the core idea. Everything else, all the engineering and mathematics and careful design, is just figuring out how to do that, throwing as efficiently and safely as possible. This principle has a name given to it by Isaac Newton back in the 1600s, long before anyone seriously dreamed of spaceflight. Newton's third law of motion. For every action, there is an equal and opposite reaction. Push on something, and it pushes back on you with equal force. You experience this constantly, though you probably don't think about it. When you walk, you push backward on the ground, and the ground pushes you forward. When you swim, you push water backward, and the water pushes you forward. When you sit in a chair, you push down on it, and it pushes up on you. The universe is full of these gentle negotiations of force. Rockets take this principle and amplify it dramatically. They take fuel, usually a combination of liquid oxygen and liquid hydrogen, or kerosene and oxygen, or some other chemistry that releases enormous energy when combined, and they burn it. This combustion happens in a chamber at the bottom of the rocket, and it produces incredibly hot gases. We're talking temperatures of around 3,000 degrees Celsius, hot enough to melt almost anything. These superheated gases want to expand. They want to spread out in every direction, the way all gases do, seeking equilibrium with the pressure around them. But the rocket engine is designed to let them expand in only one direction, downward, through a carefully shaped nozzle at the bottom of the rocket. As these gases rush out the nozzle at tremendous speed, faster than the speed of sound, sometimes much faster, they push against the rocket itself. The rocket, in turn, is pushed in the opposite direction, upward, away from Earth. This is Newton's third law, writ large in fire and thunder. You might think this sounds wasteful. After all, you're throwing all that mass, all those gas molecules, away from you, never to return. And you'd be right to think that. It is wasteful, in a sense. Every kilogram of gas expelled is a kilogram your rocket no longer has. This is why rockets are mostly fuel. A typical rocket might be 90% fuel by weight, with only 10% devoted to structure, engines, cargo, and crew. It's a bit like filling your car's gas tank and discovering that the tank takes up 90% of the vehicle, leaving just a tiny space for you to squeeze into. Not particularly efficient for daily commuting, but absolutely necessary for leaving a planet. The genius of rocket design lies in doing this mass throwing as efficiently as possible. Engineers have spent decades, lifetimes, figuring out how to squeeze every last bit of thrust from every kilogram of fuel, how to make engines lighter without making them weaker, how to structure tanks that can hold fuel at cryogenic temperatures without cracking or leaking. There's something almost artistic about a well-designed rocket engine. The way the fuel and oxidizer are injected into the combustion chamber, the precise shape of the nozzle that accelerates the exhaust gases, the cooling systems that prevent the engine from melting itself. It's engineering as poetry, written in mathematics and metal. Let's pause for a moment and appreciate that. We've taken the simple idea of pushing against something and turned it into machines capable of lifting hundreds of tons away from Earth. That's remarkable. That's humans taking a basic physical principle and bending it to our will through ingenuity and careful thought. Now, here's where things get interesting. You might assume that a rocket works by pushing against the ground or pushing against the air. Many people do think this, but that's not quite right. A rocket pushes against its own fuel. It doesn't need ground or air. In fact, rockets work better in the vacuum of space than they do in Earth's atmosphere. This seems counterintuitive at first. How can something move without pushing against anything external? But remember, the rocket is pushing against the gases it's expelling. Those gases have mass, and accelerating that mass requires force, and that force has an equal and opposite reaction that pushes the rocket forward. In space, there's no air resistance slowing the exhaust gases down. The gases can expand more efficiently, which means the engine actually becomes more effective. It's one of those delightful ironies of physics. The environment that seems most hostile to travel is actually where rockets perform best. There are different types of rocket engines, each with its own gentle trade-offs. Solid rocket boosters, like the ones used on the space shuttle, are simple and reliable. The fuel is mixed into a solid form inside the casing, and once you light it, it burns until it's gone. You can't turn it off or throttle it down. It's committed, like a candle burning steadily to its end. Liquid rocket engines, on the other hand, offer control. You can throttle them up or down, turn them off and restart them. This flexibility makes them ideal for missions that require precision. But they're more complex, with pumps and valves and plumbing that must work perfectly under extreme conditions. And then there are hybrid engines, combining solid and liquid elements, trying to get the best of both approaches. There are also ion engines, which work on entirely different principles, using electricity to accelerate ions to incredible speeds. These produce tiny amounts of thrust. You could counteract an ion engine's push with just your hand, but they can run for years, slowly, patiently building up speed. Each type has its place, its purpose, its particular beauty. There's no single best rocket engine, just as there's no single best tool. It depends on what you're trying to do, where you're trying to go, how much mass you need to move. But regardless of type, all rockets share that core principle. They throw mass backward to push themselves forward. They convert chemistry into motion, fuel into freedom. They take advantage of one of the universe's fundamental rules, equal and opposite reactions, to accomplish something that would have seemed like magic to our ancestors. Think about that for a moment as you rest there. Every rocket launch, every journey beyond Earth, relies on this beautifully simple idea. There's something almost meditative about it. Push and be pushed, expel and be lifted. Give up mass to gain altitude. The universe, as always, plays fair. It doesn't care about our dreams of reaching the stars, but it does provide the rules, clearly and consistently. And if we're clever enough, patient enough, persistent enough, we can use those rules to achieve remarkable things, including, as it turns out, leaving Earth entirely. Speaking of leaving Earth, let's talk about one of the most important concepts in space travel: escape velocity. It's a term you've probably heard before, maybe in science fiction movies or documentaries. But what does it actually mean? And why does it matter so much? Escape velocity is the minimum speed an object needs to break free from a planet's gravitational pull without any additional propulsion. For Earth, that speed is about 11.2 kilometers per second, or roughly 40,000 kilometers per hour. That's fast. Incomprehensibly fast, really. It's about 30 times faster than a passenger jet cruises. Now, here's something fascinating. Escape velocity doesn't depend on the mass of the object trying to escape. A grain of sand and a Saturn V rocket need the same speed to leave Earth. What differs is the amount of energy required to reach that speed, which very much does depend on mass. A grain of sand needs hardly any energy to accelerate to escape velocity. A rocket weighing thousands of tons needs, well, an extraordinary amount. You might think of escape velocity like a toll you have to pay to leave Earth. The toll is the same for everyone, 11.2 kilometers per second, but gathering enough currency to pay that toll is easier for some than others. But why do we need to go so fast? Why can't we just drift gently upward until we're in space? The answer lies in gravity, that persistent, patient force that's been with us since birth. Gravity is always pulling you back toward Earth. It's not a violent pull. Earth isn't grabbing at you angrily. It's more like a gentle, constant encouragement to return. Come back down, gravity whispers. Stay here where it's safe. When you jump, gravity brings you back. When you throw a ball, gravity curves its path back to the ground. Even birds, graceful as they are constantly working against gravity with every wing beat. Stop flapping, and gravity wins. For an object to escape Earth completely, to leave and never come back, it needs to be going fast enough that gravity, despite pulling on it the entire time, can never quite slow it down to zero. The object's speed decreases, yes, but it approaches zero asymptotically, never quite reaching it. By the time its speed has decreased to nearly nothing, it's so far away that Earth's gravity has become negligibly weak. It's a bit like rolling a ball up a hill that never quite levels off. If you roll it too slowly, it comes back down. But if you roll it fast enough, it keeps going, getting slower and slower, but always maintaining some forward motion. By the time it's barely crawling, it's so far up the infinite hill that the slope has nearly flattened. Interestingly, escape velocity is a threshold, not a requirement. Rockets don't actually reach escape velocity while still in Earth's atmosphere. That would be unnecessarily stressful on the vehicle, and incredibly wasteful of fuel fighting air resistance at such speeds. Instead, rockets accelerate more gently, getting to a comfortable speed, and then they continue applying thrust over time. As long as you have a source of propulsion, you can take as long as you want to leave Earth. You could, in theory, leave at a walking pace if you had enough fuel and didn't mind the journey taking a very, very long time. Escape velocity is really the speed you'd need if you wanted to leave Earth without any engines, coasting on momentum alone. It's the minimum speed for a one-time push to freedom. Different celestial bodies have different escape velocities, and this tells us something about their character. The Moon's escape velocity is only 2.4 kilometers per second, less than a quarter of Earth's. This makes sense. The Moon is smaller and less massive, so its gravity is weaker. Mars, being larger than the Moon but smaller than Earth, has an escape velocity of about 5 kilometers per second. Jupiter, that massive gas giant, has an escape velocity of 60 kilometers per second. Leaving Jupiter is much, much harder than leaving Earth. The Sun, massive beyond our easy comprehension, has an escape velocity at its surface of 617 kilometers per second, more than 0.5% of the speed of light. And on the extreme end, black holes have regions called event horizons, where the escape velocity equals the speed of light. Since nothing can go faster than light, nothing can escape. Not even light itself, which is why they're called black holes. Gravity pulls so strongly there that even the fastest possible speed isn't enough. It's the universe's ultimate prison, from which there is no escape, no matter how fast you go. But let's return to Earth, our gentle home planet, with its relatively modest escape velocity of 11.2 kilometers per second. This number has defined the challenge of spaceflight since humans first seriously considered leaving our world. Every rocket ever built has had to contend with this requirement. Every space mission has had to budget fuel, not just for reaching orbit, but for reaching the speed necessary to stay there or go beyond. This single number, 11.2, has shaped the design of spacecraft, determined which missions are feasible, and set the boundaries of human space exploration. There's something poetic about it, really. Earth's gravity, the force that keeps us grounded, that makes us feel weight, that brings falling objects to rest, is not insurmountable. It's strong, but not infinitely so. With enough speed, with enough energy, with enough careful engineering, we can overcome it. We can leave, and we have. Thousands of times now, humans have reached escape velocity and gone to the Moon. Probes have exceeded it and visited every planet in our solar system. Some spacecraft have gone fast enough to escape not just Earth, but the Sun's gravity as well, heading out into interstellar space with our messages and our hopes carried along with them. Right now, as you rest there, Voyager 1 and Voyager 2 are drifting through the space between stars, having long ago exceeded the Sun's escape velocity. They're never coming back. They're humanity's first true ambassadors to the galaxy, carrying sounds and images from Earth into the cosmic void, moving at speeds we achieved through careful planning and the gradual acceleration provided by gravity assists from the outer planets. Escape velocity is not just a speed, it's a threshold, a boundary, a doorway between being bound to a world and being free in space. Cross it, and you've left home. The mathematics of gravity still apply. Gravity reaches infinitely far, technically, but practically speaking, you've escaped its embrace. You're free to drift among the stars, slow and peaceful, a mote of dust in an ocean of darkness, carrying with you the dreams of the world you left behind. Now we move to one of the most beautifully counterintuitive aspects of space travel, orbital mechanics. This is the study of how objects move through space under the influence of gravity, and it's full of surprises, paradoxes, and elegant mathematical truths that seem almost designed to confuse us. Let's start with a simple question. What is an orbit? You might answer that an orbit is a path an object takes around a planet or star. And you'd be right, but that's not the whole story. Here's a more interesting way to think about it. An orbit is what happens when you're falling towards something, but moving sideways fast enough that you keep missing it. That's it. That's an orbit. You're falling, constantly, pulled by gravity toward the center of whatever you're orbiting. But you're also moving sideways so fast that by the time you'd reach where the planet was, the planet's curved surface has, well, curved away. So you fall past it. And then you keep falling, perpetually, in a graceful arc that never quite catches what it's chasing. The International Space Station is falling right now. It falls every second of every day. But it's also moving sideways at about 7.7 kilometers per second. And at that speed, Earth's surface curves away at exactly the rate that the station falls. The result is a circular path, a stable orbit, a state of perpetual, almost but not quite, catching Earth. Astronauts on the ISS are in free fall. They feel weightless, not because there's no gravity. There's plenty of gravity at that altitude, about 90% of what we feel on Earth's surface, but because they and their spacecraft are falling together. When you're in an elevator and the cable snaps, you briefly feel weightless because you and the elevator are falling at the same rate. Astronauts experience this constantly. They're in a very elegant, very fast elevator that never quite hits the ground. It's a bit like a beautiful, infinitely long fall, where you never have to worry about landing. Now here's where orbital mechanics gets delightfully strange. If you're in orbit and you want to catch up to something ahead of you, your instinct might be to speed up. Fire your engines forward, increase your speed, catch up. Right? Wrong. Paradoxically wrong. When you speed up in orbit, you raise your orbit. You go higher. And in a higher orbit, you actually move more slowly. So by speeding up, you end up going slower. Meanwhile, the thing you were trying to catch, in its lower, faster orbit, pulls ahead of you even more. To catch something ahead of you in orbit, you have to slow down. Fire your engines backward, decrease your speed, lower your orbit. In the lower orbit, you'll move faster and you'll catch up. It's backwards, it's counterintuitive, it's orbital mechanics. This is why astronauts have to study orbital dynamics so carefully. Intuition from living on Earth's surface doesn't apply in space. Up is slow, down is fast, backward is forward, in a sense. There's a specific speed you need to maintain a circular orbit at a given altitude. Too slow, and you fall back toward Earth. Too fast, and your orbit becomes elliptical, carrying you higher before you eventually come back down. Much too fast, and you escape orbit entirely. For a low Earth orbit, like where the ISS resides, that speed is about 7.8 kilometers per second. That's just slightly slower than Earth's escape velocity, which makes sense. You're not quite going fast enough to leave, but you're going fast enough to keep missing the ground. Orbits are governed by Kepler's laws, discovered in the early 1600s by Johannes Kepler, a mathematician who studied the motions of planets with painstaking care. His laws are beautiful in their simplicity. First, orbits are ellipses, not perfect circles. Every orbit has the massive object it's orbiting at one focus of the ellipse. This means orbits can be nearly circular, or they can be stretched out into long, narrow ellipses, but they're never quite perfect circles. Second, objects move faster when they're closer to what they're orbiting and slower when they're farther away. This is because of conservation of angular momentum, a concept that ensures certain properties stay constant as an orbit progresses. Third, the time it takes to complete an orbit is related to the size of the orbit by a specific mathematical relationship. Larger orbits take longer to complete. The Moon takes about 27 days to orbit Earth. The ISS takes about 90 minutes. The relationship is precise and mathematical, a cosmic clockwork. These laws apply everywhere. They govern planets orbiting stars, moons orbiting planets, spacecraft orbiting anything with mass. They're universal, in the truest sense of the word. Let's pause here and appreciate the elegance of this. The universe has rules, and those rules are mathematical. And once we figured out those mathematics, we could predict exactly how objects move through space. We could plan missions, calculate trajectories, and send spacecraft to distant worlds with extraordinary precision. Voyager 2 was launched in 1977 with a trajectory calculated to visit Jupiter, Saturn, Uranus, and Neptune. The spacecraft followed this path perfectly, arriving at each planet within minutes of the predicted time, despite traveling for years through the vast emptiness of space. That's orbital mechanics. That's mathematics made real. There's also something called the Oberth effect, which is another one of those delightfully counterintuitive orbital mechanics principles. It states that if you want to gain the most energy from a given amount of fuel, you should burn that fuel when you're moving fastest. Typically, when you're closest to the object you're orbiting. This seems backwards at first. You'd think burning fuel when you're moving slowly would give you more benefit. But no. The mathematics work out such that a small velocity change, when you're already moving fast, produces a much larger change in energy than the same velocity change when you're moving slowly. It's used constantly in space missions. Spacecraft wait until they're closest to a planet, moving at their maximum speed, and then they fire their engines. This slingshots them onward with much more energy than they could have gained by burning fuel anywhere else in their orbit. Gravity assists, also called gravitational slingshots, are another beautiful application of orbital mechanics. A spacecraft approaches a planet, enters its gravitational influence, swings around behind it, and exits with more speed than it entered with. The spacecraft steals a tiny bit of the planet's orbital momentum. The planet slows down by an infinitesimally small amount, so small it would take sensitive instruments measuring for years to detect, and the spacecraft speeds up significantly. It's like running alongside a very, very slowly moving train, grabbing hold for a moment and being flung forward. The train barely notices. You gain tremendous speed. Voyager 2 used gravity assists at Jupiter, Saturn, and Uranus to reach Neptune. Without these assists, the mission would have been impossible with 1970s rocket technology. The planets themselves became part of the spacecraft's propulsion system, their gravity harnessed through careful planning and precise navigation. Orbital mechanics also explains why there's no such thing as stationary in space. Everything is moving. Earth orbits the Sun. The Sun orbits the center of the Milky Way galaxy. The galaxy itself is moving through space. There's no fixed reference point, no cosmic anchor that sits still while everything else moves around it. When astronauts feel weightless in space, they're not in zero gravity. They're in free fall, falling alongside their spacecraft, falling around Earth in an endless, graceful arc. Gravity is still there, still pulling, still patient and persistent. But because everything is falling together, the astronauts feel like they're floating. It's an interesting illusion, really. Weightlessness and perpetual falling are the same thing. Freedom from gravity's pull and falling under gravity's influence are identical experiences. Right now, thousands of satellites are in orbit around Earth, each following its own carefully calculated path. Some are in low orbits, zipping around the planet every 90 minutes. Some are in higher orbits, taking hours to complete a circuit. Some are in geosynchronous orbit, 22,000 miles up, where the orbital period matches Earth's rotation. So the satellite hovers over the same spot on the ground, apparently motionless. All of them are falling. All of them are moving sideways fast enough to keep missing Earth. All of them are graceful examples of orbital mechanics in action, and all of these elegant, mathematical, sometimes counterintuitive principles were waiting in the universe long before humans discovered them. They governed the motions of the moon and planets for billions of years before we looked up and wondered why things moved the way they did. The universe has always been mathematical. We just needed time to learn its language. Let's talk about staying alive in space, which turns out to be significantly more complicated than one might initially think. You see, space doesn't just lack convenient places to land. It lacks almost everything necessary for human life. Air, water, comfortable pressure, comfortable temperature, protection from radiation. Space is, in nearly every measurable way, trying to kill you. Not maliciously, of course. Space isn't hostile in an intentional sense. It's just profoundly indifferent to your continued existence. It's an environment that never evolved with life in mind, where the basic conditions that make Earth habitable simply don't exist. So if we want to send humans into this void, we have to bring Earth with us, in a sense. We have to create a tiny bubble of Earth-like conditions inside a metal shell, and maintain that bubble perfectly while traveling through an environment that wants very much to make that bubble stop existing. This is what life support systems do. They create and maintain a livable environment where none would naturally exist. Let's start with the most immediate need: air. Specifically, breathable air, which on Earth we take for granted in the most absolute way possible. You've been breathing unconsciously since you were born. Your body handles it automatically, about 15 times a minute, every minute, of every day, forever. You don't think about it unless something goes wrong. In space, everything about air requires thought, planning, and constant technological vigilance. Humans need oxygen to breathe. We breathe in air, extract the oxygen, use it to fuel cellular processes, and exhale carbon dioxide as waste. On Earth, this works beautifully because the atmosphere is constantly refreshed. Plants consume carbon dioxide and produce oxygen through photosynthesis. The atmosphere is massive enough that the carbon dioxide from individual human breaths disperses harmlessly. The system balances itself. In a spacecraft or space station, there are no plants. Well, there are some experimental plants, but not nearly enough to recycle the air for a crew. And the atmosphere is tiny, just the air inside the habitable volume of the spacecraft. If you breathe in a sealed room long enough, you'll gradually use up the oxygen and fill the air with carbon dioxide. Eventually, you'll suffocate, not from lack of air, but from too much of your own exhaled waste. So spacecraft need systems to remove carbon dioxide and replenish oxygen. There are several approaches, each with its own gentle elegance. The simplest method is to carry extra oxygen and use chemical scrubbers to remove carbon dioxide. The scrubbers contain materials, often lithium hydroxide, that react with CO2 and pull it out of the air. Meanwhile, oxygen is released from pressurized tanks or generated through chemical reactions. This works well for short missions, like the Apollo flights to the moon. You carry enough consumables for the trip, use them up, and come home before you run out. For longer missions, like aboard the International Space Station, a more sophisticated approach is needed. The ISS uses the Environmental Control and Life Support System, or ECLSS, which does something remarkably clever. It recycles. Water vapor and carbon dioxide are removed from the air. The water vapor is condensed and purified for drinking and other uses. The carbon dioxide is combined with hydrogen in a reaction that produces water and methane. The water is kept, the methane is vented overboard. Separately, water is split into hydrogen and oxygen through electrolysis. The oxygen goes back into the air. The hydrogen is used in that earlier reaction with carbon dioxide. It's a cycle, a gentle choreography of chemical processes that mimics, in a simplified way, what Earth's biosphere does naturally. It's not perfect. Some water and air are still lost and must be resupplied from Earth. But it's remarkably efficient. The ISS can recycle about 90% of its water. Think about that for a moment. The water you drink aboard the ISS today might have been someone's exhaled breath, or sweat, or urine days ago. It's been filtered, purified, and reconstituted into pure water. Astronauts joke that yesterday's coffee becomes tomorrow's coffee, and they're not entirely wrong. It sounds unpleasant perhaps, but really it's quite beautiful. It's a testament to human ingenuity, turning waste back into resource, creating a closed loop where nothing is truly lost, only transformed. Water, speaking of which, is crucial for more than drinking. Humans need water for hydration, yes, but also for hygiene, for food preparation, for cooling systems, for radiation shielding. Water is heavy. 1 liter weighs 1 kilogram. So minimizing water needs while still keeping astronauts healthy is a constant balancing act. On the ISS, water is precious. Astronauts don't take long showers. They don't have showers at all, actually. Instead, they use wet wipes and rinseless soap, carefully collecting every drop of water they use. Laundry isn't done. There's no washing machine. Clothes are worn until they're too dirty, then discarded. It sounds uncomfortable, and it is, slightly. But astronauts adapt. They report that after a while, you stop noticing. The lack of a hot shower becomes normal. The careful conservation of every resource becomes second nature. Temperature control is another vital function. In space, temperature regulation is challenging because there's no air to conduct heat away from your body or your spacecraft. On Earth, if you overheat, you sweat, and the air carries that heat away through convection. In space, with no air, convection doesn't work. Spacecraft use radiators to dump excess heat into space through radiation. These radiators are large panels, usually mounted on the exterior of the spacecraft, that glow in infrared, carrying away the heat generated by humans, electronics, and sunlight hitting the spacecraft's surface. They're essential. Without them, the spacecraft would gradually cook itself. But the spacecraft can also get too cold, particularly when in Earth's shadow or when traveling far from the sun. So, heaters are needed as well. The balance is delicate, constantly adjusted by automated systems that monitor temperatures throughout the spacecraft and make tiny corrections to maintain a livable environment. Food is another challenge. Humans need to eat, obviously, and the food needs to be nutritious, shelf-stable for months or years, light enough to launch affordably, and ideally, not completely awful to eat. Early space food was notoriously bad, freeze-dried blocks and tubes of paste that technically contained nutrients but were joyless to consume. Modern space food is much better. There are rehydratable meals, thermostabilized pouches that can be heated, and even some fresh fruit on resupply missions. Astronauts have a menu, they can choose what they want to eat, and while it's not quite restaurant quality, it's genuinely edible. There's something poignant about eating in space, though. Every meal is packaged, every bite carefully planned months in advance. The simple pleasure of picking an apple from a tree, or biting into bread still warm from the oven, or tasting something you decided to make on a whim. These ordinary joys are absent. Everything is controlled, scheduled, optimized. And yet, astronauts adapt to this too. They find joy in their meals, they look forward to their favorite packaged dishes, they share food with crewmates. Humans are remarkably resilient, emotionally and physically. We can find contentment in the strangest circumstances. Waste management, to put it delicately, is also a concern. Humans produce waste, and in space, that waste can't simply be flushed away. It has to be contained, processed, and either recycled or stored for disposal. The space toilet is a marvel of engineering, using airflow instead of water to move waste into collection containers. It's not the most dignified device ever created, and astronauts report that using it takes some getting used to. But it works. Some waste is jettisoned, loaded onto cargo ships that burn up during re-entry. Some is processed and recycled. Remember, urine becomes drinking water through the magic of filtration and chemistry. The ISS is, in a very real sense, a system for keeping humans alive by constantly transforming and recycling the elements that make up a human-friendly environment. All of these systems, air, water, temperature, food, waste, have to work continuously, perfectly, for months or years. A failure in any one system could be catastrophic. Redundancy is built in wherever possible. Backup systems have backup systems. Still, astronauts train extensively on troubleshooting and repair, because when you're hundreds of kilometers from Earth, you can't wait for a repair crew to arrive. The life support systems on spacecraft represent some of the most impressive engineering humanity has achieved. They're complex, interdependent, carefully designed, and absolutely essential. They turn an inhospitable void into a place where humans can live, work, and even, sometimes, feel at home. They let us take a little piece of Earth with us into the darkness, carrying the conditions of our birth world like a fragile, precious gift, keeping it safe while we explore realms that were never meant for us, but were perhaps always waiting for us anyway. Now we come to something less pleasant but equally important, the dangers of space. We've talked about the life support systems that keep you alive. But what are they protecting you from? What makes space so hostile? Let's talk about radiation, that invisible, patient threat that suffuses the cosmos. On Earth, we're protected by two remarkable shields. The first is our atmosphere, a 100-kilometer thick blanket of air that absorbs and scatters much of the dangerous radiation that comes from space. The second is Earth's magnetic field, generated by the swirling molten iron in our planet's core, which deflects charged particles from the sun and cosmic rays from deeper space. Together, these shields make Earth's surface a relatively safe place to exist. The radiation that does make it through is manageable. Our bodies have evolved mechanisms to repair the occasional DNA damage from background radiation. Life on Earth has always been bathed in a gentle level of radiation, and we've adapted to cope with it. But beyond Earth's protective embrace, radiation becomes a serious concern. There are several sources of radiation in space, each with its own character and danger. First, there's solar radiation, charged particles streaming constantly from the sun in what's called the solar wind. This wind is made of protons and electrons ejected from the sun's outer layers, traveling through space at hundreds of kilometers per second. When these particles hit Earth's magnetic field, they're deflected toward the poles, where some of them interact with the upper atmosphere to create the aurora, those beautiful, shimmering curtains of light in the polar skies. The aurora is, in a sense, visible evidence of Earth's magnetic shield in action, protecting us from radiation that would otherwise harm us. In space, without that shield, solar radiation becomes a hazard. It can damage electronics, degrade solar panels, and harm living tissue. Astronauts in low Earth orbit are partially protected because they're still within Earth's magnetic field, but they still receive higher radiation doses than people on the ground. Then there are solar flares and coronal mass ejections, violent eruptions on the sun's surface that send huge bursts of radiation and charged particles into space. These events are sporadic and somewhat unpredictable. A large solar flare pointed at Earth can cause spectacular auroras, disrupt radio communications, and damage satellites. For astronauts in space, a major solar event could be deadly. The radiation from a large flare or coronal mass ejection could deliver a fatal dose in hours if the astronauts were exposed without protection. Spacecraft have designated storm shelters, areas with extra shielding where crew can take refuge during solar events. But even so, the risk is real. Beyond solar radiation, there's also galactic cosmic radiation, high-energy particles from outside our solar system, produced by distant supernovas and other violent cosmic events. These particles have been accelerated to incredible speeds, sometimes approaching the speed of light. When they strike matter, they can penetrate deeply, passing through spacecraft walls, through spacesuits, through human bodies. Galactic cosmic rays are constant and unavoidable. They represent a background radiation that's always there, always slowly accumulating damage. Over long periods, this exposure increases the risk of cancer, cataracts, and other health issues. There's no perfect shield against them. They're too energetic, too penetrating. You can reduce exposure with shielding, but this has limits. Heavy materials like lead block radiation well, but they're heavy, and launching mass into space is expensive. Also, when high-energy particles hit heavy nuclei, they can produce secondary radiation that's sometimes worse than the original particle. Water and hydrogen-rich materials are actually better shields in some ways, which is why spacecraft designers consider filling walls with water or using polyethylene rather than metal for radiation protection. Still, for long missions, trips to Mars, for instance, radiation remains one of the most challenging problems. A journey to Mars takes 6 to 9 months each way. During that time, astronauts would be exposed to radiation levels far higher than any human has experienced for sustained periods. The long-term health effects are uncertain. We can model and predict, but we won't know for sure until someone actually makes the journey. It's a sobering thought. These future Mars explorers We'll be pioneers not just in exploration, but in understanding what deep space does to the human body over time. Let's pause for a moment and acknowledge the quiet courage that requires to sign up for a mission knowing that you're accepting risks that aren't fully understood, that might shorten your life or harm your health in ways that won't be apparent for years. That's a different kind of bravery than the obvious danger of sitting atop a rocket. It's a slower, more patient kind of courage. Beyond radiation, there are other dangers. There's the vacuum of space itself. Without pressure, human blood would start to boil. Well, not exactly boil like water on a stove. More accurately, dissolved gases in your blood would come out of solution, forming bubbles. This is called ebulism, and it's as unpleasant as it sounds. You wouldn't explode, though. That's a Hollywood myth. The human body is actually fairly robust. Your skin and tissues can contain internal pressure for a brief time, but you would lose consciousness in about 15 seconds as oxygen left your lungs and bloodstream. You'd suffocate quickly. If you were somehow returned to pressure within a minute or two, you'd likely survive, though with some tissue damage, but survive much longer than that in vacuum. No, death would follow, quiet and absolute. This is why spacesuits are so crucial. They're not just clothing, they're miniature spacecraft providing pressure, oxygen, temperature control, radiation shielding, and protection from micrometeorites. A spacesuit is a wearable life support system, keeping you alive in an environment that very much wants you dead. Micrometeorites, speaking of which, are another danger. Space is full of tiny particles, remnants of asteroids and comets, traveling at incredible speeds. At orbital velocities, even a paint fleck can hit with the energy of a bullet. These impacts happen constantly. The ISS has been hit thousands of times by micrometeorites, leaving tiny craters in its solar panels and external surfaces. So far, no impact has caused a catastrophic failure, but it's a constant risk. Designers build in redundancy and shielding, but the threat remains. Space is full of tiny projectiles, all moving at velocities that make them incredibly destructive despite their size. There's also the psychological challenge of space travel. Being confined in a small space with the same few people for months, far from Earth, with no quick escape if something goes wrong, or if you simply can't stand your crewmates anymore, this takes a toll. Astronauts are carefully screened for psychological stability and are trained in conflict resolution and stress management. Even so, tension arises. People get irritable, frustrated, homesick. They miss Earth, the blue sky, fresh air, the ability to walk outside without a spacesuit. They miss variety, spontaneity, privacy. The ISS is not a large place. You can't go for a walk to clear your head. You can't step away from your work or your crewmates in any meaningful way. Isolation and confinement are real psychological dangers, especially on longer missions. Future missions to Mars will involve years away from Earth, with communication delays of up to 20 minutes each way. You couldn't have a real-time conversation with mission control or your family. Messages would be recorded, sent, and you'd wait for responses to arrive long after you'd moved on to other thoughts. There's a loneliness to that which is hard to imagine fully, a slow, patient distance that grows with every kilometer you travel from home. And yet, astronauts manage. They adapt. They find joy in their work, in the view of Earth from orbit, in the strange and wonderful experience of weightlessness. They form bonds with their crewmates. They video call their families. They maintain routines that provide structure and comfort. Humans are remarkably resilient. We can find meaning and even happiness in circumstances that seem impossibly difficult. We adapt to what we must adapt to. Space is dangerous, yes. It's radiation and vacuum and isolation and 1,000 ways to die if systems fail. But it's also navigable. With care, with technology, with courage and preparation, humans can survive there. We have survived there. We've lived in space continuously for over 2 decades now, aboard the ISS. Space may not want us there, but it doesn't get a vote. We've decided to go anyway. Let's talk about moments. Specific moments in human history when we did something for the first time. something that seemed impossible until it wasn't. Moments that changed how we think about ourselves and our place in the universe. We'll start with 1961, with a man named Yuri Gagarin. On April 12th of that year, Gagarin climbed into a small spacecraft called Vostok 1, perched atop a rocket at the Baikonur Cosmodrome in Kazakhstan. He was 27 years old. He'd been selected from thousands of candidates to be the first human to attempt what no one had done before: leave Earth entirely, orbit the planet, and return alive. At 9:07 Moscow time, the rocket engines ignited. Gagarin reportedly said, "Poyakali, let's go," as the rocket lifted off. For 108 minutes, he orbited Earth, the first human to see our planet from space, to experience weightlessness, to leave the atmosphere and live to describe it. He saw Earth as a sphere, blue and white and beautiful, floating in darkness. He saw the thin line of atmosphere at the horizon, the fragile shell that makes life possible. He experienced weightlessness, noting that it was pleasant, not frightening. He returned safely, landing in a field in the Soviet Union, where he was greeted by startled farmers who couldn't quite believe the man in the orange spacesuit who'd just parachuted from the sky. Gagarin became an instant hero, celebrated around the world. He'd proven that humans could survive space, travel. The door was open. Less than a month later, on May 5, 1961, Alan Shepard became the first American in space, though his flight was suborbital, a 15-minute arc that took him just beyond the edge of space before falling back to Earth. It was a start. John Glenn followed in 1962, becoming the first American to orbit Earth, spending nearly 5 hours in space aboard Friendship 7. His mission was broadcast live, and millions watched, transfixed, as America's astronaut circled the globe. The pace accelerated. More missions, more firsts. The first woman in space, Valentina Tereshkova, in 1963. The first spacewalk, Alexei Leonov, floating outside his spacecraft in 1965, tethered by a cord, drifting in the void. The first spacewalk by an American, Ed White, a few months later, who reportedly said that being ordered to return to his spacecraft was the saddest moment of his life. These early missions were experiments, tests, learning experiences. Spacecraft were primitive by modern standards. Computers were massive and weak. There were no laptops, no GPS, no satellite networks. Astronauts flew with slide rules and star charts. They relied on training, skill, and courage. And then came the moon. On July 20th, 1969, not quite 8 years after Gagarin's first orbit, Neil Armstrong and Buzz Aldrin descended to the lunar surface in the Lunar Module Eagle, while Michael Collins orbited overhead in the Command Module Columbia. Armstrong climbed down the ladder, placed his boot on moon dust, and said those now famous words: "That's one small step for man, one giant leap for mankind." Actually, what he'd intended to say was, "one small step for a man," but the transmission was unclear, and history recorded it with the slight grammatical oddity. No matter, the meaning was clear. Humans had reached another world. Armstrong and Aldrin spent just under a day on the moon. They planted a flag, collected rock samples, set up scientific instruments, and took photographs. They hopped around in the low gravity, moving with an awkward, bouncing gait that looked almost playful. Then they launched back to orbit, rejoined Collins, and returned to Earth. The audacity of it is hard to appreciate now. They traveled 384,400 kilometers to another celestial body using 1960s technology. They landed on a world with no air, no magnetic field, temperature extremes from boiling to freezing, where the slightest mistake in any of thousands of systems would mean death. And they did it successfully. Between 1969 and 1972, 12 humans walked on the moon across 6 Apollo missions. They explored different regions, collected hundreds of kilograms of lunar rocks, drove lunar rovers across the surface, and demonstrated that humans could work effectively in such an alien environment. They hit golf balls that flew impossibly far in the low gravity. They planted flags that still stand, though the harsh sunlight has probably bleached them white by now. And then we stopped. The last moon landing was Apollo 17 in December 1972. No human has returned since. That chapter of exploration closed, left to wait patiently for whatever comes next. Why did we stop? The reasons are complex, political, economic, cultural. The initial motivation for going to the moon was largely driven by Cold War competition between the United States and Soviet Union. Once the US had clearly won by landing first, public and political interest waned. The missions were expensive. People had other concerns. The future they'd imagined, moon bases, Mars missions, human exploration throughout the solar system, didn't materialize. Instead, human spaceflight turned toward low Earth orbit. The Space Shuttle program began in 1981, a reusable spacecraft that could launch like a rocket and land like a plane. Over 30 years and 135 missions, shuttles carried satellites into orbit, serviced the Hubble Space Telescope, and built the International Space Station piece by piece. The space station itself is another remarkable achievement. Construction began in 1998 and continued for over a decade, assembling a complex structure of modules, solar panels, and life support systems in orbit. It's been continuously inhabited since November 2, 2000. Over 2 decades of humans living in space without interruption. The ISS is a laboratory, a home, a symbol of international cooperation. Multiple nations contributed modules and systems. Astronauts from many countries have lived aboard it. It orbits Earth 16 times a day, traveling at 7.7 kilometers per second. A testament to what humans can build when we work together toward a common goal. From the ISS, astronauts conduct experiments that can only be done in microgravity. They study how crystals form without gravity to distort them, how flames behave in weightlessness, how plants grow without up or down being meaningful concepts. They study themselves, how their bodies adapt to long-term weightlessness, how their bones weaken and muscles atrophy despite rigorous exercise, how fluid shifts in their bodies without gravity to pull it down into their legs. This research isn't just academic curiosity, it's preparation. If we're going to send humans to Mars or beyond, we need to understand how to keep them healthy during months or years in space. The ISS is teaching us that. Meanwhile, uncrewed spacecraft have explored the solar system extensively. Probes have visited every planet, landed on asteroids and comets, descended through the atmospheres of distant worlds, and sent back images and data that continue to reshape our understanding of our cosmic neighborhood. Voyager 1 and 2, launched in 1977, have now left the solar system entirely, entering interstellar space. They carry golden records with sounds and images from Earth, greetings in multiple languages, music from various cultures, photographs showing the diversity of life and human achievement. Their messages in bottles cast into the cosmic ocean, unlikely to ever be found but sent anyway, as gestures of hope and introduction. The Mars rovers have explored the red planet's surface, drilling into rocks, analyzing soil, searching for evidence of past life. Curiosity and perseverance trundle slowly across Martian plains, autonomous robots guided by instructions from Earth, exploring a world humans have dreamed of visiting for generations. We've learned that Mars once had liquid water on its surface. We've found organic molecules in Martian soil. We've discovered that Mars has ice at its poles and probably beneath its surface. It's a world that might have once been habitable, that might still harbor life in subsurface aquifers or in some protected niche we haven't yet discovered. The Cassini spacecraft orbited Saturn for 13 years, studying its rings, its atmosphere, its dozens of moons. It discovered liquid water oceans beneath the ice crusts of Enceladus and possibly Titan. These moons might harbor life, simple microbial life perhaps, living in dark oceans warmed by tidal heating, never seeing sunlight, but thriving nonetheless. New Horizons flew past Pluto in 2015, showing us that this distant dwarf planet is far more complex and geologically active than anyone expected. its heart-shaped glacier, its mountains of water ice, its thin atmosphere, all were surprises, reminders that the solar system still holds countless wonders we haven't yet witnessed. All of these missions, crewed and uncrewed, represent humanity slowly, patiently learning about the universe. Each is a footnote in a story that's still being written, a story of exploration driven by curiosity and wonder. We've come remarkably far in just over 60 years since Gagarin's first orbit. We've gone from barely reaching space to landing on the moon, building permanent habitats in orbit, and sending probes to the edge of the solar system and beyond. But we've also only just begun. The achievements so far are impressive, yes, but they're also just the opening chapters of what could be a very long book. The rest of the story is still waiting to be written, one mission, one discovery, one gentle step at a time. Here's where things get personal. Let's talk about what it's actually like to live in space, day to day, aboard the International Space Station. What does a normal day look like when there's no normal? When down is a direction that doesn't exist, and when you're traveling at 7.7 kilometers per second. Astronauts aboard the ISS follow a schedule because humans need structure, even, perhaps especially, in the most unusual circumstances. They wake up at roughly the same time each day, though day is a curious concept when you orbit Earth 16 times in 24 hours, experiencing 16 sunrises and sunsets. They wake up in sleeping bags attached to walls. In weightlessness, beds are unnecessary. You can sleep oriented in any direction. There's no need for a mattress because there's no gravity pressing you down. You just float, gently held in place by a sleeping bag zippered to contain you. Some astronauts report sleeping remarkably well in space. Without gravity compressing your spine, you float in perfect comfort. No pressure points, no need to shift position. Others find it disorienting at first, their bodies confused by the absence of down, by the strangeness of having your arms float up if you don't tuck them into the sleeping bag. After waking, there's breakfast. Food is stored in packages, some requiring water to rehydrate, some eaten as is. There's coffee, if you want it, sipped from a pouch through a straw. Without gravity, liquids don't pour. They form floating spheres that drift lazily through the air. Drinking requires sucking liquid from sealed containers. It's awkward at first, but becomes second nature. There are no tables. You don't sit down to eat because sitting requires gravity. Instead, you float near your food, which is held in place by Velcro or magnets or your hand. Crumbs are dangerous. They float into air vents or electronics or your eyes, so bread is generally avoided in favor of tortillas. Sticky food is preferred because it stays on utensils. After breakfast, work begins. Astronauts spend their days conducting experiments, maintaining the station, exercising, and communicating with Earth. Experiments cover an astonishing range, studying protein crystal formation, growing plants, monitoring their own body's responses to weightlessness, testing new technologies, observing Earth's climate and geography. Maintenance is constant and essential. The ISS is a complex machine operating in a hostile environment. Things break. Filters need changing, computers need updating, experiments need monitoring. Astronauts are not just scientists, they're mechanics, electricians, plumbers, and handymen, trained to fix nearly anything that might malfunction. Exercise is mandatory. In weightlessness, your muscles and bones don't need to work as hard. Without the constant loading that gravity provides, they begin to atrophy. Bones lose density, muscles weaken. If astronauts didn't exercise vigorously every day, they'd return to Earth unable to walk, their bodies too weak to support their own weight. So astronauts spend about 2 hours daily on treadmills and resistance machines, harnesses holding them down against the treadmill since there's no gravity to do it naturally. They lift and push and pull, working hard to maintain the strength they'll need when gravity returns. Washing up is an interesting challenge. There are no showers, no running water, no drains for water to run down. Instead, astronauts use wet towels, carefully rationing water, wiping themselves clean. For hair, they use rinseless shampoo and towels. It's not luxurious, but it's functional. The bathroom, as mentioned earlier, uses airflow to replace gravity. It's perhaps not the most dignified aspect of space travel, but it works, and after, the initial awkwardness becomes just another part of the routine. Clothing is worn for days before being discarded. Laundry is impossible. Water is too precious to waste washing clothes. So astronauts wear the same outfits repeatedly until they become too dirty or smelly, and then they discard them, loading them onto cargo ships that will burn up during re-entry. There's a certain acceptance required here. You will smell. Your crewmates will smell. The station will smell. A mixture of human sweat, machine oil, recycled air, and the peculiar odor of the station itself, which astronauts sometimes describe as smelling like ozone or burnt metal. You adapt. Olfactory fatigue sets in. You stop noticing. Between work sessions, astronauts have breaks. They float to a window. The cupola offers the best views and stare at Earth passing below. This never gets old, they report. Every view is different. Deserts and oceans, cities lit up at night, storms swirling over the Pacific, the aurora shimmering at the poles, the Sahara's golden sands, the Amazon's green sprawl. Earth from space is achingly beautiful. The thinness of the atmosphere is startling. Just a delicate blue line at the horizon, all that stands between life and the void. Astronauts often report that seeing Earth from space changes them, instills a sense of perspective and fragility. Our world is small, it's finite, it's precious. All of human history, all our conflicts and triumphs occur on this one beautiful isolated sphere. This perspective has a name, the overview effect. It's the cognitive shift that occurs when you see Earth whole, when you realize viscerally, not intellectually, but emotionally, that we're all on this planet together, that borders are human inventions, that the atmosphere is shared, that we're all floating through space on the same rock. Many astronauts return from space with a deeper sense of environmental concern, a desire to protect Earth, a frustration with how we treat our only home. Having seen it from outside, having witnessed its beauty and fragility firsthand, they can't unsee it. Meals are communal when possible. The crew floats together, eating and talking, sharing their day. Food is one of the few pleasures available in space, and astronauts look forward to their meals, especially favorite dishes or care packages from Earth with special treats. Communication with family happens regularly through video calls. The delay is minimal in low Earth orbit, so conversations are nearly real-time. Astronauts talk to their children, see their homes, hear about the ordinary events of life on Earth. These calls are lifelines, connections to the world below, reminders of what they're missing and what they'll return to. There's also time for personal activities. Astronauts read, watch movies, play musical instruments, take photographs. Chris Hadfield famously recorded a music video for David Bowie's Space Oddity aboard the ISS. Scott Kelly read an entire novel aloud over video to his twin brother's daughter on Earth. These human moments, these expressions of personality and creativity, are essential for psychological health. Sleep comes again, another cycle completed. The sleeping bag, the gentle containment, the strange sensation of floating while unconscious. Dreams in space are reportedly vivid, sometimes involving flying or falling, the brain trying to make sense of the constant acceleration signals from your inner ear. Day after day, week after week, month after month, the rhythm continues. Wake, eat, work, exercise, eat, work, rest, eat, sleep. It's routine, yet profoundly strange. It's boring, yet incredible. It's work, yet privilege. Not many humans have experienced what these astronauts experience daily. Fewer than 700 people have been to space. Fewer than 20 have traveled beyond low Earth orbit. Each person who goes adds to humanity's collective experience, expands the boundaries of what we know about living beyond Earth. The ISS has been called a stepping stone to Mars and beyond. That's true. We're learning lessons there that will be essential for longer missions. But it's also valuable in its own right. It's a laboratory producing research that benefits people on Earth. It's a symbol of cooperation, built and operated by nations that sometimes disagree on Earth but work together in space. And it's a home. Not a comfortable home, not a luxurious home, but a home nonetheless. The astronauts who live there for months at a time form bonds, create routines, find joy in small things, and adapt to circumstances that would have seemed impossible to previous generations. They're pioneers, not in the dramatic sense of conquering new frontiers, but in the quiet, patient sense of learning how to live somewhere new, of making the strange familiar, of proving that humans can thrive, not just survive, in environments we weren't evolved for. They're teaching us that space, inhospitable as it is, can be inhabited, that humanity's future, if we choose it, might extend beyond this single planet. That home is not just Earth, but wherever humans are willing to work hard enough to make it so. Let's talk about now. What's happening in space at this very moment as you rest there listening? What missions are underway? What robots are exploring? What plans are being made for the years ahead? Right now, the International Space Station continues its endless orbit, home to typically 7 astronauts from multiple nations. It's aging, modules launched over 20 years ago, but still functional, still productive. Plans are being discussed for its eventual deorbiting, probably sometime in the 2030s, when it will be intentionally crashed into a remote part of the Pacific Ocean. Nothing lasts forever, not even humanity's greatest orbital achievement. But other stations are planned. China has built Tiangong, its own space station, which became operational in 2022. It's smaller than the ISS, but growing, with additional modules planned. China has its own crewed space program, independent of the ISS partnership, and has been steadily, patiently building capability and experience. Private companies have entered space in a way that would have seemed like science fiction a few decades ago. SpaceX, founded by Elon Musk, has developed rockets that land themselves after launching, returning to Earth to be refueled and reused. This was considered nearly impossible for years. Rockets were expendable, too stressed by launch to be worth recovering. But SpaceX proved it could be done. Their Falcon 9 boosters now routinely return to landing pads or drone ships at sea, touching down with elegant precision, ready to fly again. It's made spaceflight significantly cheaper. Reusability, it turns out, works for rockets just as it does for airplanes. SpaceX's Dragon capsule carries cargo and crew to the ISS. Boeing's Starliner is another crewed vehicle, though it's had development challenges and is still working toward regular operational flights. These commercial crew vehicles mean the United States no longer relies solely on Russian Soyuz spacecraft to reach the ISS, a capability that was lost when the Space Shuttle retired in 2011 and took years to re-establish. The Moon is, once again, a focus of attention. NASA's Artemis program aims to return humans to the lunar surface, with the first crewed landing planned for the mid-2020s. Unlike Apollo, which involved quick visits, Artemis plans sustainable exploration, a lunar gateway station orbiting the Moon, reusable landers, extended surface missions. The first woman and first person of color will walk on the Moon through Artemis. The program aims to establish a presence near the Moon's south pole, where permanently shadowed craters might contain water ice, a crucial resource for future exploration. Why return to the Moon? Several reasons. It's closer than Mars, making it a testing ground for technologies and techniques needed for more distant journeys. It has resources that could be used in space, water for life support and rocket fuel, minerals for construction, and it remains scientifically interesting, with many questions about lunar geology and history still unanswered. Mars, of course, remains the ultimate near-term goal for human exploration. Multiple nations and private entities have Mars ambitions. NASA plans human missions to Mars sometime in the 2030s or 2040s. SpaceX has more aggressive timelines, with Elon Musk suggesting crewed missions could happen in the 2020s, though many experts are skeptical of that timeline. Getting to Mars is hard. The journey takes 6 to 9 months with current propulsion technology. You can't come home immediately. Orbital mechanics dictate that launch windows between Earth and Mars occur only every 26 months when the planets are properly aligned. So a Mars mission would likely involve about 30 months away from Earth, 6 to 9 months traveling. There, about 18 months on the surface, waiting for the return window, and another 6 to 9 months traveling back. That's a long time to be far from home, far from help, in an environment where a single major system failure could be fatal. But the challenges are not insurmountable. We have the physics figured out. We understand orbital mechanics, life support, radiation protection. It's a matter of engineering, money, political will, and accepting risk. Several robotic missions are preparing the way. NASA's Perseverance rover is collecting samples of Martian soil and rock, which a future mission will retrieve and return to Earth for detailed analysis. These samples might contain evidence of past Martian life, if such life ever existed. The Ingenuity helicopter, which hitched a ride with Perseverance, has proven that powered flight is possible in Mars's thin atmosphere. This opens possibilities for aerial exploration, for vehicles that can fly over obstacles and survey terrain from above. There's also quiet work being done on in situ resource utilization, the fancy term for using resources you find where you are, rather than bringing everything from Earth. On Mars, this might mean extracting water from ice, producing oxygen from the carbon dioxide atmosphere, or using Martian soil to make bricks for construction. These aren't fantasies. They're engineering problems with solutions being tested now, in labs on Earth and in limited ways on Mars itself. They're steps toward making Mars not just a place we visit, but a place where humans could potentially live. Asteroid mining is another area of growing interest. Asteroids contain metals, iron, nickel, platinum group metals, in concentrations that would be extremely valuable. More importantly for space exploration, some asteroids contain water ice, which can be split into hydrogen and oxygen for rocket fuel. If we could mine asteroids, establishing fuel depots in space, we wouldn't need to launch fuel from Earth's deep gravity well for every mission. We could refuel in space, making journeys to distant destinations much more practical. Several companies are working on asteroid mining technology, though no one has successfully mined an asteroid yet. The technical challenges are immense: identifying valuable asteroids, reaching them, extracting resources in weightlessness, and returning those resources to where they're needed. But again, these are engineering problems, not physics impossibilities. Difficult, certainly. Expensive, absolutely. But potentially profitable and strategically important for expanding human presence beyond Earth. Looking slightly further ahead, there's serious discussion of missions to Jupiter's moon Europa and Saturn's moon Enceladus, both of which have subsurface oceans that might harbor life. These missions would search for biosignatures, chemical or physical evidence of living processes. Finding life elsewhere in our solar system, even simple microbial life, would be one of the most profound discoveries in human history. It would answer the ancient question of whether we're alone, at least partially. It would suggest that life is common in the universe, not a fluke that occurred only once on Earth. It would change how we see ourselves and our place in the cosmos. Closer to home, space tourism is becoming real. Companies like Blue Origin and Virgin Galactic offer brief trips to the edge of space, a few minutes of weightlessness, a view of Earth's curvature against the black of space. These are expensive, hundreds of thousands of dollars per seat, but prices may decrease as the technology matures and competition increases. SpaceX has taken tourists to orbit, to the ISS, and plans tourist missions around the moon. These are multi-million-dollar experiences, but they're happening. Space is slowly, gradually becoming accessible to those who aren't professional astronauts. Will space tourism become affordable for average people? Maybe, eventually. Airlines were once luxury services only the wealthy could afford. Now millions of people fly routinely. Perhaps space will follow a similar trajectory, century by century, decade by decade, becoming more accessible, more routine, more woven into the fabric of human civilization. Or perhaps not. Perhaps space will remain difficult, expensive, and dangerous, limited to professionals and the very wealthy. The future isn't predetermined. It depends on choices we make: technological development, political will, societal priorities, economic considerations. What's certain is that humanity's relationship with space is evolving. We're no longer just visitors. We're beginning to establish presence, to build infrastructure, to plan for long-term activities beyond Earth. Whether this leads to widespread space settlement or remains limited to research and resource extraction, only time will reveal. But the direction is clear. We're not stopping at having been to the moon decades ago. We're continuing, slowly and patiently, to push outward, to explore, to learn, to expand the boundaries of what's possible. The story of space exploration is far from over. In many ways, it's just beginning. Now, let's let our imagination drift further. Beyond the next decade or two, beyond current plans and near-term missions, what might humanity accomplish in space? What dreams might we realize in the coming century or centuries? Mars is the obvious first step for sustained human presence beyond Earth. It's close, by cosmic standards. It has resources. It has a 24-hour day cycle, which would help with human circadian rhythms. It has seasons, weather, polar ice caps, canyons and mountains and plains to explore. A human settlement on Mars, a permanent base, a colony, perhaps eventually a self-sustaining civilization, has been dreamed about for generations. What would it take to actually establish one? First, someone would have to go there and survive, live on Mars for months or years, prove that it's possible, learn the challenges that can't be predicted from afar. These first inhabitants would live in prefabricated habitats, probably buried under Martian soil for radiation protection. They'd recycle air and water with extreme efficiency. They'd grow some food in greenhouses or hydroponics, supplemented by supplies from Earth. Their lives would be difficult, constrained, full of work and maintenance and careful resource management. It would not be comfortable. It would be pioneering in the truest sense, living on the edge of survival, with little margin for error, in an environment that is, at every moment, trying to kill you. But over time, infrastructure would build. More habitats, better life support systems, expanded food production, mining operations to extract water and minerals from Martian soil, solar panels or nuclear reactors for power, manufacturing capability to produce tools and spare parts locally rather than importing everything from Earth. Eventually, perhaps, the colony could become self-sufficient, able to survive even if supply ships from Earth stopped arriving. That's a crucial threshold. True independence, the point at which Mars is not just an outpost, but a new branch of human civilization. How long would this take? Decades, certainly. Probably centuries to reach true self-sufficiency. Mars lacks many things Earth has: a magnetic field, a thick atmosphere, an easily accessible biosphere. Making Mars comfortable for humans would require either massive technological adaptation or slow, patient transformation of the planet itself. Terraforming Mars, altering its atmosphere, temperature, and environment to make it Earth-like, has been discussed extensively in science fiction and increasingly in serious scientific literature. Could it actually be done? Maybe. The ideas exist. You could release greenhouse gases to warm the planet, warm enough and the polar ice would sublimate, thickening the atmosphere. Introduce photosynthetic microbes to slowly produce oxygen over centuries. Crash ice-rich asteroids into Mars to deliver water and add to the atmosphere's mass. These processes would take not decades, but centuries, possibly millennia. You wouldn't live to see Mars transformed. Your grandchildren wouldn't. But perhaps your distant descendants might walk on a Mars with a breathable atmosphere, liquid water on the surface, and life introduced from Earth taking root in new soil. It's an ambitious vision, almost impossibly so. But ambition has driven human achievement throughout history. We've done things that seemed impossible: flight, space travel, landing on the moon. Perhaps with enough time and determination, terraforming Mars is possible too. Beyond Mars, the asteroid belt offers resources, millions of asteroids, ranging from small rocks to objects hundreds of kilometers across, containing metals, water, and minerals. These could be mined, their resources used to build structures in space without launching material from Earth's gravity well. Imagine a future where spacecraft and space stations are built in orbit using asteroid-derived materials, where fuel is produced from asteroid water, where permanent habitats exist not on planets, but in space itself, rotating to produce artificial gravity, home to people who've never set foot on a planet. These space habitats, sometimes called O'Neill cylinders, after physicist Gerard K. O'Neill, who popularized the concept, could be enormous, kilometers long, housing thousands or millions of people, with interior surfaces landscaped with parks and rivers and cities. They'd orbit the sun, perhaps clustered near asteroid mining operations or at gravitationally stable points called Lagrange points. It sounds like science fiction. Maybe it is. Maybe it will always remain speculative. But the physics works. The concepts are sound. It's a matter of engineering, of assembling resources, of deciding that such a future is worth pursuing. Looking even further out, there's the outer solar system. Jupiter's moons, Europa, Ganymede, Callisto, Saturn's moons, Enceladus, Titan. These are worlds in their own right, each unique, each potentially habitable in some form. Titan is particularly intriguing. It's the only moon in the solar system with a substantial atmosphere. Its surface has lakes and rivers, though filled with liquid methane and ethane rather than water. It's a strange cold world, minus 180 degrees Celsius, but it has complex organic chemistry happening naturally, making it a fascinating target for research and possibly even colonization. Living on Titan would require fundamentally different technologies than Mars. The cold is extreme. The atmosphere is nitrogen and methane. But there's atmosphere. You wouldn't need a pressure suit, just insulation and oxygen. And the organic chemicals there could potentially be used as fuel or feedstock for manufacturing. Beyond our solar system lies everything else. The galaxy contains hundreds of billions of stars, many with planets. Some of those planets are probably habitable. The nearest confirmed exoplanet in a potentially habitable zone is Proxima Centauri b, about 4.24 light-years away. That's close by galactic standards, our nearest stellar neighbor, but it's also incomprehensibly far. Light takes 4.24 years to travel that distance. Our fastest current spacecraft would take tens of thousands of years to get there. Interstellar travel is, with current technology, essentially impossible for humans. We can't survive journeys lasting thousands of years. We don't have propulsion systems that could reach even a fraction of light speed. We don't have ways to shield against cosmic radiation for such durations. We don't have self-sustaining life support for multi-generational ships. But could we develop such technologies? Perhaps. Concepts exist. Generation ships where multiple generations live and die during the journey, their descendants eventually arriving at the destination. Cryogenic hibernation, if we could make it work safely. Embryo ships carrying frozen embryos and artificial wombs, with AI systems raising the first generation upon arrival. There's also the possibility of sending not humans, but our consciousness, uploaded into machines that could survive the journey and build bodies upon arrival. Or we might never physically travel to other stars, but instead send probes, tiny spacecraft accelerated by lasers to fraction of light speed, arriving decades later to beam back information. These ideas range from plausible to speculative to purely theoretical. But humans have a way of turning speculation into reality, given enough time. What's certain is that interstellar travel, if we ever achieve it, is a challenge for future centuries, not decades. It requires technologies we don't yet have, resources we haven't yet marshaled, and a commitment spanning more than individual lifetimes. But standing in your backyard and looking up at the stars, it's hard not to wonder. Those lights are suns like ours. They probably have planets. Some of those planets might harbor life. And if we're patient enough, clever enough, determined enough, might we someday visit them? Or will we always remain bound to our solar system, reaching outward within our sun's domain, but never quite bridging the vast darkness between stars? Time will tell. The universe isn't going anywhere. The stars will wait, patient as always, while we figure out if we have the will and the way to reach them. Let's slow down and ask a question that might seem strange. Why do we do this? Why do we spend enormous resources, take significant risks, and dedicate brilliant minds to leaving Earth? The practical justifications exist. Space research produces technologies that benefit life on Earth. Satellite communications, GPS, weather prediction, medical devices, materials science advances. The ISS enables experiments that couldn't be done on Earth. Asteroid mining might provide resources. Mars colonies could serve as backup for human civilization if something catastrophic happens to Earth. These are real benefits. They're worth mentioning. But if we're honest, they're not the whole story, maybe not even the main story. We go to space because we're curious, because humans have always explored, always pushed beyond known boundaries, always asked what's over there, and then gone to find out. This curiosity seems built into us, woven into human nature at some fundamental level. Our ancestors migrated out of Africa, spreading across continents despite not knowing what lay ahead. They crossed oceans in fragile boats, not knowing if there was land on the other side. They climbed mountains to see what was at the top. They explored, not because it was practical, but because the unknown beckoned and they couldn't resist. Space is the latest frontier in that ancient pattern. It's the next horizon, the next question mark on the map. We go because not going feels like giving up, like accepting limits we're not ready to accept. There's also the survival argument, though it's grim to contemplate. Earth won't last forever. Someday, billions of years from now, but someday, the sun will expand into a red giant, engulfing Mercury and Venus and possibly Earth. Long before that, the sun's increasing luminosity will make Earth uninhabitable. Life here has an expiration date. More immediately, there are existential risks: asteroid impacts, supervolcano eruptions, pandemics, climate change, nuclear war. Earth has experienced 5 mass extinctions in its history. There's no guarantee there won't be a 6th. Having humans and human civilization spread across multiple worlds makes us more resilient as a species. If something catastrophic happens to Earth, we might still continue elsewhere. This is sometimes called the backup plan, justification for space colonization. Earth is precious, and we should protect it, but it's also prudent to not have all our eggs in one planetary basket. But beyond survival and curiosity, there's something else, something harder to articulate, but perhaps more important. Going to space enlarges us, metaphorically speaking. It expands our sense of what's possible, what we're capable of, where we belong in the universe. When astronauts look at Earth from space and experience the overview effect, that shift in perspective where borders disappear and our world looks fragile and unified, they're accessing a truth that's hard to see from the ground. We're all on this planet together. Our differences are trivial compared to our shared humanity and shared fate. Space exploration also produces moments of collective achievement that transcend national boundaries. The moon landing was an American achievement technically, but it was also a human achievement. We came in peace for all mankind, the plaque left on the moon reads. That wasn't jingoism, it was recognition that some accomplishments belong to everyone. The ISS is another example. 16 nations working together to build and operate something extraordinary. In space, cooperation has proven more productive than competition. Different nations with different political systems and sometimes tense relationships on Earth work together smoothly in orbit. There's something hopeful in that. Space also inspires. Children who watch rocket launches dream of becoming astronauts, scientists, engineers. They study hard, pursue technical careers, push themselves to understand difficult concepts because they want to be part of this grand adventure. Not all of them end up in aerospace, but society benefits from having more people passionate about science and engineering. And there's the sheer wonder of it. Space is beautiful. Earth from orbit is beautiful. The Moon, Mars, Saturn's rings, galaxies spiraling through darkness, these inspire awe, that emotion humans feel when confronted with something vast and incomprehensible, yet real. Awe is good for us, psychologically. It makes us feel part of something larger than ourselves. It reminds us that the universe is bigger and stranger than our daily concerns. It provides perspective, humility, a sense of connection to something transcendent. Space exploration produces that awe regularly. Every image from the James Webb Space Telescope showing galaxies billions of light years away. Every video of Earth slowly rotating beneath the ISS. Every successful landing on Mars. These moments remind us that we live in an astonishing universe and that we're capable of learning about it, of exploring it, of participating in its vastness. There's also the question of meaning. Why are we here? What's the purpose of human existence? These are old questions without clear answers, but space exploration offers a possible answer. We're here to learn, to explore, to understand, to spread life and consciousness through a universe that otherwise is mostly empty and dark. Maybe that's presumptuous. Maybe the universe doesn't need us, doesn't care if we explore or stay home. But we care. We derive meaning from the attempt, from pushing against our limits, from turning our faces toward the unknown and deciding to venture into it, despite the risks. Carl Sagan wrote about the pale blue dot. Earth, as seen from billions of miles away by Voyager 1, a tiny speck in the vastness of space. He noted that every human who ever lived, every civilization, every triumph and tragedy occurred on that mote of dust suspended in a sunbeam. It's a humbling image, but it's also inspiring. That tiny dot produced consciousness, curiosity, and civilizations capable of sending spacecraft to the edge of the solar system. That dot produced us, and now we're looking back at it from the places we've ventured to, seeing our home in context, understanding our place in the universe a little better. Space exploration is about more than science and technology. It's about identity, meaning, aspiration. It's about choosing to be a species that explores rather than stagnates, that reaches for possibilities rather than accepting limits. Will we colonize Mars? Mine asteroids? Travel to other stars? Maybe, maybe not. But the attempt itself, the fact that we try, says something important about what it means to be human. We could stay on Earth forever, safe and limited, but we don't seem built that way. We seem built to push boundaries, to ask, what's next? And then find out. Space is simply the latest incarnation of that ancient impulse, transferred from terrestrial horizons to cosmic ones. And as long as humans exist, as long as we look up at the night sky and feel the tug of curiosity and wonder, we'll keep going out there, slowly and patiently, one mission at a time, bringing our dreams with us into the darkness. What is space travel? It's the question that brought us here tonight, whispered softly at the beginning, like a child asking if we could really reach the stars. And after wandering through rocket engines and orbital mechanics, through life support systems and radiation hazards, through historic achievements and future dreams, we find ourselves gently circling back to where we began, still wondering. We've learned that leaving Earth requires extraordinary speed, 11.2 kilometers per second at least, and that achieving that speed requires rockets that are mostly fuel, burning violently to push us upward. We've explored how orbits are just perpetual falling, how astronauts live in carefully maintained bubbles of Earth-like conditions while surrounded by vacuum and radiation. We've remembered the courage of Gagarin, Armstrong, and countless others who ventured into the unknown. We've contemplated Mars bases, asteroid mining, and perhaps someday the stars themselves. Space travel is not just physics and engineering, though it's certainly both. It's not just survival systems and orbital calculations, though those are essential. It's a testament to human curiosity, stubbornness, and refusal to accept limits. It's us looking at the impossible and quietly saying, let's try anyway. Maybe space will always remain difficult, expensive, and dangerous. Maybe we'll never achieve the futures imagined in science fiction. Vast colonies, casual interplanetary travel, starships voyaging between worlds. Maybe we'll remain primarily earthbound, with only the occasional brave soul venturing beyond. Or maybe not. Maybe our descendants will look back at this era, these early decades of space exploration, the way we look back at the Wright Brothers' first flights. Maybe what seems extraordinary now will seem quaint and primitive to future generations who grew up on Mars or in orbital habitats. Maybe the universe is full of life, and we'll soon find evidence of it beneath Europa's ice or in the oceans of Enceladus. Maybe we're alone, the only consciousness to arise in this corner of the galaxy, which would make our continued existence and exploration even more precious. Maybe that's the whole point. The universe doesn't provide simple answers. It provides mysteries, questions, frontiers to explore. And we, stubborn and curious as we are, keep exploring. So, with all of this in mind, are you still awake? If you are, I hope it's not because I was too interesting. Though, if I was, well, at least you've learned something about humanity's grandest adventure, the attempt to leave our homeworld and venture into the cosmic ocean beyond. And if you're already halfway to dreamland, may your thoughts drift peacefully among the stars, floating gently in the darkness, like an astronaut in orbit. Before you drift off completely, I'd love to know where you're listening from and what time it is in your part of the world. Drop a comment and share. Are you perhaps dreaming of space yourself, planning a career in aerospace, or just someone who finds the cosmos strangely comforting? If you found this gentle journey through space travel relaxing or informative or both, please do consider giving this video a like and subscribing to Sleepy Science Student. It's a small gesture that helps me keep bringing you more calming, curious content from the world of science and beyond. Thank you for joining me on this journey beyond Earth. Sleep well, dream deep, and may your imagination carry you gently through the cosmos. Remember, somewhere above you, right now, astronauts are floating in orbit, seeing 16 sunrises today, living proof that humans can thrive even in the most unlikely places. The stars are still there, patient as always, waiting to see what we do next. Good night.